Hello, Tech Unplugged. Welcome to your personalized deep dive. You've presented us with a really fascinating collection of information on Snowflake, the cloud-based data warehousing platform. Today, we're embarking on a journey to understand not just what Snowflake is, but its fundamental impact on how businesses handle data in the modern era. Think of it as moving beyond the traditional constraints of data management into a new realm of flexibility and scalability.
Absolutely. And you've gathered a rich set of insights here. Our aim today is really to synthesize these, providing you with a clear understanding of Snowflake's core architectural principles and its unique capabilities. We'll be sort of connecting the dots, trying to reveal why its approach is considered, well, a significant leap forward in data warehousing.
Okay, sounds good. Let's start by looking at where Snowflake came from. Apparently, it was founded back in 2012
Hmm?
by some folks with deep roots in the database world, former data architects from Oracle, actually.
That's right. And their goal was to build something specifically, for the cloud. And interestingly, that name Snowflake, it's apparently inspired by their shared passion for winter sports.
Huh, okay. Skiing databases.
Mm-hmm.
But the key thing is, they weren't just trying to tweak old tech, right?
Exactly. The foundational insight here is that they aim to transcend the inherent limitations of, well, both legacy on-premises data warehouses and the initial wave of cloud-based solutions. They even characterize their own architecture as fourth generation, which highlights a pretty substantial evolution in data platform design. This wasn't just about putting an old model in a new environment. It was like a ground-up rethinking.
And this rethinking led to their unique three-layered architecture, right? We're talking about the storage layer, the compute layer, and this cloud services layer. Can you walk us through why this is such a departure?
Yeah, the crucial element is the disaggregation of storage and compute. It's really the key. See, traditional systems often tightly couple these, which leads to challenges when you need to scale one, but maybe not the other.
Right, like needing more processing power but not more storage space, or vice versa.
Precisely. So Snowflake's storage layer leverages cost-effective cloud object storage. Think of it like a vast, centralized, and secure repository. All your data resides there, compressed and encrypted. Then, the compute layer consists of independent virtual warehouses.
Okay, so those are where the actual queries run.
Exactly. These are where the queries are actually processed. And the beauty is you can scale these up or down or, have multiple running concurrently without affecting the underlying storage at all. And finally, that cloud services layer, it acts as the intelligent management hub, the brain, if you will. It handles everything from user authentication and query optimization to metadata management.
So it's definitely more than just sticking a database in the cloud. This separation sounds like it addresses some really fundamental challenges around scalability and resource utilization. I remember reading something about shared disk versus shared nothing architectures. How does Snowflake's approach fit in or differ?
That's a key distinction. So shared disk systems, they can be simpler to manage sometimes, but they often hit performance bottlenecks with lots of concurrent users. Shared nothing systems offer great scalability, but can come with increased complexity, in terms of data distribution and management.
Okay.
Snowflake takes a kind of hybrid approach. The data is in that central shared storage layer we talked about, but the compute resources, those virtual warehouses, they are completely independent, like shared nothing. This allows for that crucial independent scaling of storage and compute.
Okay. So if you suddenly need a lot more processing power for, say, a complex analysis.
You just spin up a larger warehouse or more warehouses. You don't need to move or duplicate your terabytes and terabytes of data first.
Right. So you get the benefit of centralized data management with the flexibility of distributed computing resources. That makes a lot of sense, both for independent scaling and, I guess, the cost optimization aspect. You're only paying for the compute you actively use.
Exactly. And the concurrency without contention, that's huge for organizations with lots of data analysts hitting the system at once.
Yeah, avoiding those slowdowns.
Precisely. The pay-per-second billing for compute is, well, a game changer for many. You're no longer locked into paying for provision capacity that might just sit idle half the time. This allows for much more agile and, frankly, cost-effective data analysis. And the ability for multiple teams, maybe marketing and finance, to run queries simultaneously on the same data without performance degradation is critical for data-driven decision-making across the whole organization.
Okay, let's move on a bit to what Snowflake actually offers in terms of functionality. It's a software as a service model, a SaaS model. For someone using it, what are the practical implications of that, like day to day?
Well, in essence, it means Snowflake handles the heavy lifting of infrastructure management. You don't need to worry about server provisioning, patching, software upgrades, or backups. Snowflake takes care of all that stuff behind the scenes.
So it significantly reduces the operational overhead.
Massively. It allows teams to focus purely on working with their data and, extracting insights rather than managing infrastructure.
And it's designed to work across multiple major cloud providers, AWS, Azure, and Google Cloud Platform. That's not something you see everywhere.
No, it's a big deal. This multi-cloud capability provides significant flexibility. It allows organizations to choose the cloud provider that best suits their needs, or maybe leverage existing relationships or pricing deals. It also adds a layer of resilience and can help mitigate vendor lock-in risks, which is always a concern.
We've already touched on scalability, but the sources suggest it's almost on demand, like virtually limitless for both storage and compute. Is that really the case?
That's the promise of a purely cloud-native architecture, yeah? Snowflake can handle massive data volumes without you having to pre-plan storage capacity down to the last gigabyte. And when your processing needs spike, maybe during month-end recording, you can scale your virtual warehouses up or out with minimal disruption.
Now, for the more technically inclined listeners, Snowflake supports ACID compliance, which is obviously crucial for data integrity. However, it's often noted that it's particularly well-suited for OLLP workloads. Could you clarify why? What's the distinction there?
Sure. So while Snowflake absolutely ensures ACID properties for data consistency, its architecture is fundamentally optimized for online analytical processing, OLA. This means it's designed for complex queries and analysis over large data sets, your typical data warehousing scenarios, right? Business intelligence, reporting, data science explorations.
Right.
While it can handle some transactional style operations, its real strength lie in providing high throughput and performance for these analytical workloads, rather than the, say, super low latency, high concurrency demands of traditional OLTP, online transaction processing databases like you'd use for an e-commerce checkout system.
Got it. So analytics is where it really shines. What about the language it uses? It supports standard ANSI SQL, which is widely familiar.
Exactly. The adherence to the ANSI SQL standard means that most data professionals, analysts, engineers, they'll have a relatively smooth learning curve. They can leverage their existing skills.
And it can handle both structured and semi-structured data formats natively, like JSON or XML.
Yep. That's another significant advantage in today's kind of diverse data landscape. The ability to ingest and query both structured data, like your classic relational tables, and semi-structured data, like JSON, Avro, Parquet, XML, without complex upfront transformations or separate systems is really powerful.
The sources also highlighted some pretty unique features: time travel, zero-copy clone, and robust data sharing capabilities. These sound incredibly powerful, almost like science fiction for data.
Huh. Yeah, they are kind of game changers. Time travel allows you to access historical versions of your data just as it existed at points in the past. This enables recovery from errors like if someone accidentally drops a table or for auditing changes over time. Think of it as rewinding your data state.
Wow, okay, that sounds incredibly useful. And zero-copy clone.
Zero Copy Clone lets you create instant, independent copies of your databases, schemas, or tables. And crucially, without incurring any additional storage costs until you actually start making changes to the clone. This is invaluable for development, testing, creating isolated environments for experiments, things like that.
Without duplicating massive amounts of data.
Exactly. And then the secure data sharing capabilities allow you to share live data with other Snowflake accounts without the traditional complexities and delays of building data pipelines or constantly copying data back and forth.
And it seems like there's a real focus on reducing operational overhead, too. The platform largely handles things like indexing, partitioning, and other physical design considerations automatically.
That's correct. Snowflake is designed to be very low touch from an administrative perspective. The cloud services layer, that brain we mentioned, automates many of these traditionally manual and time-consuming tasks.
Though I did see a note about potential benefits from maybe some query optimization in very complex cases.
Yes, absolutely. While Snowflake's optimizer is very sophisticated, for highly complex analytical queries or, truly massive data sets, understanding how Snowflake processes data and perhaps applying some best practices in query design can still lead to performance gains. It's not completely magic.
Fair enough. And finally, on features, the automatic workload isolation. That sounds critical for ensuring consistent performance. when you have multiple users or processes running concurrently.
Absolutely critical. Snowflake automatically isolates the compute resources of different virtual warehouses. So, a resource-intensive data load or transformation running in one warehouse won't impact the speed or responsiveness of, say, business intelligence queries running in another warehouse, even if they're accessing the same underlying data tables.
Okay, we have a good grasp of the fundamentals now. Let's talk about actually getting started. There's a free trial available, which is always a plus.
Yep, always good to try before you buy.
Yeah.
And the registration process is self-service, pretty easy to get going.
Once you're in, what's the primary way to interact with Snowflake? Is it mainly through the web UI, the web interface?
Yes, for many users, the Snowflake Web User Interface, or Web UI, is the primary point of interaction. It's designed to be fairly intuitive and provides access to all the core functionalities of the platform through a graphical interface running queries, managing objects, monitoring usage.
And then there's this hierarchical structure of objects. Account, then database, then schema, and then within schemas, you have things like tables, views, stages, and so on. How does this organization work? What's the logic?
Think of it as a logical container system, really. The account is the top-level organizational unit for your company or team. Within an account, you can have multiple databases. These are essentially logical groupings of schemas. Schemas, in turn, are logical groupings of your actual database objects like tables, views, and also things like stages, which are named locations for storing data files.
So databases and schemas are basically logical namespaces to keep things organized and manage permissions.
Exactly. This hierarchy helps you organize your data assets logically, manage security permissions effectively, and control access in a granular way.
And through the web UI, you can perform basic operations like creating these containers, databases, schemas, tables, and even uploading small amounts of data directly.
Precisely. The web UI offers user-friendly tools for creating these logical structures and for performing initial data loading, maybe for testing or for smaller data sets, right through your browser. It's handy for quick tasks.
Okay. Now, I noticed a somewhat maybe counterintuitive point about constraints, like primary keys and unique keys. While you can define them, Snowflake primarily only enforces not NLL constraints during data loading. Why that approach? Seems a bit different.
It is a bit different from traditional databases, yeah. This is a deliberate architectural choice, really focused on optimizing for high-speed, high-volume data ingestion. Enforcing complex integrity constraints like unique keys or foreign keys during the load process itself can introduce significant performance overhead, slowing things down.
Ah, so it's a trade-off for speed.
Exactly. Snowflake prioritizes getting the data in quickly and efficiently, especially at scale. You can still define these other constraints, primary key, unique key, foreign key, for documentation purposes, and analytical tools downstream might use them, but the responsibility for ensuring that kind of data quality often shifts. It shifts to the ETL or ELT, the data transformation processes that happen after the initial loading. The not NOL constraint is enforced at load time because it's pretty fundamental.
That makes sense, prioritizing speed for large-scale loading. So when we talk about actually moving data into Snowflake in bulk, the copy into command seems to be the key tool, and this involves using these things called stages.
Exactly right. For loading any significant amount of data, the copy into command is a primary workhorse. It efficiently pulls data files from designated locations called stages and loads them into your Snowflake tables. Stages can be either internal to Snowflake, which means Snowflake provides and manages a secure storage area for you, or they can be external.
External meaning.
Meaning they point to your existing cloud storage buckets on services like Amazon S3, Azure Blob Storage, or Google Cloud Storage, so you can load data directly from where it might already live.
Okay, and there's a variety of supported file formats like CSV and Parquet with options for compression. I even saw some information suggesting that certain combinations, like maybe compressed Parquet, perform better in terms of loading speed.
Yes, the choice of file format and compression definitely can have a noticeable impact on loading performance. Parquet, being a columnar format, is generally very efficient for analytical queries and often for loading, too. Compression algorithms like Snappy, often used with Parquet, or gzip, commonly used with CSV, can significantly reduce file sizes, leading to faster data transfer over the network.
So smaller files load faster, makes sense.
Right. And some internal tests or community benchmarks do indicate that Snappy compressed Parquet often yields the quickest loading times in many scenarios. However, Snowflake themselves often recommend starting with maybe CSV or gzip compressed CSV just because it's widely compatible and sometimes easier to generate.
Gotcha. It was also mentioned that the size of the virtual warehouse you're using for the loading operation directly influences the speed. More compute power equals faster loading for the same amount of data.
Absolutely. That's a critical point for performance tuning. A larger virtual warehouse simply has more underlying compute nodes, more processing power. This allows it to process and load data in parallel much more effectively, which can significantly reduce the overall loading time, especially for really substantial data sets. Double the warehouse size, you might have the load time, roughly speaking.
Okay. And for more continuous automated data ingestion, there's something called Snowpipe. That sounds like a key component for near real-time data pipelines.
Precisely. Snowpipe is Snowflake's continuous data ingestion service. It's designed for exactly that scenario. Once you've set it up, it essentially monitors your cloud storage locations, those external stages, for new files arriving. And then it automatically loads them into Snowflake with minimal latency, often within minutes. It's ideal for scenarios where you need near real-time access to incoming data, like IoT events or application logs.
Let's dive a bit deeper into virtual warehouses then. We know they provide the compute power for queries and loading, but their elasticity, the ability to resize them on the fly, and crucially, the auto-suspend resume feature that seems like a major advantage, especially for cost control.
That elasticity is absolutely central to Snowflake's value proposition, yes. You can dynamically resize a virtual warehouse, make it bigger for demanding workloads like complex machine learning model training, and then scale it back down afterwards to manage costs. And the auto-suspend feature is brilliant. It automatically pauses the warehouse when it's idle for a configurable period, so you literally stop paying for compute resources you aren't actively using.
And it just wakes up again when a query comes in.
Exactly. Auto-resume brings it back online almost instantly when a new query is submitted to it. It's seamless for the end user, but saves a lot on the bill.
And the concept we touched on earlier, having multiple independent warehouses accessing the same data simultaneously, that really underscores the workload isolation benefit. Different teams or processes can operate without stepping on each other's toes.
Exactly right. You can provision separate virtual warehouses tailored specifically to different workloads. Maybe you have a large warehouse for the nightly ETL batch processing, smaller ones for departmental BI dashboards, and perhaps another dedicated one for the data science team's explorations. Each operates independently, ensuring consistent performance and optimized resource utilization for its specific purpose, all drawing from that same single source of data in the storage layer.
And for really high concurrency needs.
For very high concurrency demands, Snowflake offers multi-cluster warehouses, typically in their Enterprise Edition or higher. These can automatically scale out horizontally, adding more clusters of the same size as query load increases, and then scale back in as the load decreases. It's dynamic concurrency management.
Okay, that makes sense. Now, data rarely goes straight from loading into its final analytical form. Transformation is usually required. It sounds like Snowflake supports both common patterns, ETL and ELT workflows, and offers specific tools like streams and tasks to help facilitate this.
That's correct. Snowflake is flexible and accommodates both extract, transform, load, ETL, where transformation happens before loading, and extract, load, transform, ELT, where raw data is loaded first and then transformed within Snowflake. ELT is actually very common with Snowflake due to its scalable compute. And yes, streams are fundamental for change data capture, or CDC.
Change data capture.
Tracking changes?
Yeah.
Streams allow you to track all the changes, inserts, updates, deletes made to your source tables over time. They essentially record the delta. This is super useful for building incremental data pipelines. And tasks are Snowflake's native scheduling capability. They let you schedule the execution of SQL statements, including calls to stored procedures.
So you can automate your transformation logic right inside Snowflake.
Exactly. You can set up tasks to run on a schedule like every hour, or trigger them based on certain conditions, perhaps when a stream has new data.
And these tasks can be orchestrated to create more intricate data processing sequences, task trees, I believe they were called.
Yes. Task trees allow you to define dependencies between tasks. You can build complex, multi-step data workflows where, say, Task B only runs after Task A successfully completes. It lets you build pretty sophisticated data pipelines entirely within the Snowflake environment.
We also encountered external tables earlier when talking about stages. The ability to query data that's actually residing in external cloud storage, like S3, without loading it into Snowflake first. That seems incredibly useful, especially for dealing with data lakes or just massive data sets you only need to query occasionally.
Absolutely. External tables are a powerful feature for that exact reason. They essentially provide a metadata layer over your data sitting in external storage. You define the table structure and point it to the files in S3 or Azure Blob or GCS. Then you can query this data using standard SQL just as you would a regular Snowflake table.
But the data doesn't move.
The data stays where it is in your external storage. Snowflake reads it on demand when you query the external table. This is invaluable for exploring vast amounts of data in your data lake, perhaps before deciding what to actually load and transform. It's also great for integrating data from diverse sources without the overhead and cost of ingestion, and for certain data governance scenarios where data needs to remain in a specific location.
Okay, shifting gears a bit. Security is obviously paramount when dealing with cloud-based data platforms. Snowflake appears to have a pretty comprehensive security framework, starting with role-based access control, or RBAC. How does that work?
Indeed, RBAC is really the cornerstone of Snowflake's security model. It's how you control access. You define roles like analyst, developer, admin, and then you grant specific privileges to those roles. Privileges like select on a table or usage on a warehouse or create schema in a database. Then you grant those roles to your users or even to other roles to create a hierarchy. It allows for very granular control over who can see what and do what.
And for enhancing user account security itself, there's multi-factor authentication, MFA.
Yes, and this is crucial. Enabling MFA adds that critical second layer of security beyond just a password. Users have to provide an additional verification factor, usually from an authenticator app on their phone. This significantly reduces the risk of unauthorized access, especially if user credentials get compromised somehow.
We'll come back to why that's so important in a moment. Data masking is another interesting feature mentioned, allowing for the obfuscation or hiding of sensitive data for unauthorized users.
Right. Dynamic data masking provides protection by allowing you to define policies that automatically mask sensitive information. Think credit card numbers, social security numbers, personal identifiers. The policy dictates that users with certain roles see the masked version, like asterisks, while privileged users see the actual raw data. This is essential for maintaining data privacy and meeting compliance requirements like GDPR or CCPA.
And of course, encryption both for data at rest and while it's being transmitted, that's just table stakes, right?
Absolutely fundamental. Snowflake encrypts all customer data at rest by default using strong industry-standard encryption algorithms. You don't even have to turn it on. It's always on. And all communication between clients, like the web UI, drivers connectors, and the Snowflake service is secured using TLS encryption in transit.
Network policies to restrict access to only trusted IP ranges and detailed audit logs to track all activity for security monitoring and compliance are also part of the standard security posture.
Correct. Network policies allow administrators to define lists of allowed or blocked IP addresses, adding another layer of perimeter security. Only connections from trusted locations can get through, and the audit logs provide a detailed, immutable record of virtually all actions performed within your Snowflake environment, logins, queries run, objects created or modified. These are crucial for security investigations and meeting regulatory compliance obligations.
Speaking of compliance, Snowflake adheres to numerous major industry standards like GDPR, IPCA for healthcare data, ISO 27001, SOC1, SOC2, SOC3.
That's right. Snowflake undergoes regular, rigorous, independent audits and certifications to validate its compliance with these and other key regulatory frameworks. This provides assurance to organizations, especially those handling sensitive data, across various regulated industries like finance, healthcare, and government.
Now, you mentioned MFA being crucial. There was a concerning point in the materials about recent threat campaigns, specifically one group dubbed UNC5537, targeting Snowflake customer instances. It appears these attacks leverage stolen user credentials. What's the critical takeaway here for anyone using Snowflake or, frankly, any cloud service?
The paramount lesson really is the shared responsibility model for cloud security. It cannot be stressed enough. Even with a platform like Snowflake that has robust built-in security features, the customer must implement and maintain strong security practices on their end. The investigation into those UNC5537 incidents, as publicly reported by Snowflake and security firms, found no evidence of a compromise of Snowflake's internal systems or platform itself.
So it wasn't a breach of Snowflake.
No, according to the findings. Instead, the attackers used compromised customer credentials, usernames, and passwords that were likely obtained through separate means, like infostealer malware on user machines, or purchased from dark web marketplaces from previous unrelated breaches. This underscores the absolute necessity of enabling multi-factor authentication on all user accounts, especially any accounts with elevated privileges like administrators or service accounts, and enforcing the use of strong, unique passwords managed through a password manager ideally.
What were the attackers actually doing once they got in with stolen credentials?
The observed attack patterns typically involved logging in, creating temporary storage locations called stages, using the copy Y into command to pull sensitive data from the customer's tables into those stages, and then using another command, GET, to download or exfiltrate that stage data out of Snowflake to attacker-controlled storage. It highlights that while Snowflake provides a secure foundation, securing your own access points and monitoring activity remains your critical responsibility. Basic security hygiene is non-negotiable.
That's a vital point. Cloud security is always a partnership. Okay, let's shift gears slightly to programmability. Snowflake allows you to extend its functionality using user-defined functions, UDFs, and also stored procedures.
Yes, this adds a lot of power and flexibility. UDFs allow you to define custom functions to use within your SQL queries. You can write them in SQL itself for simpler logic, or use JavaScript for more complex operations. Java UVFs are also supported, though they require a bit more setup with JAR files. This lets you encapsulate reusable logic and extend the built-in capabilities of the SQL language within Snowflake.
I noticed some distinctions mentioned in how, say, SQL and JavaScript UDFs handle aspects like NL values or something called volatility.
Correct. There are nuances. SQL UDFs tend to be more declarative, focusing on the input-output relationship. JavaScript UDFs offer more imperative control, including how NUL inputs are specifically handled. You can also define JavaScript UDFs as deterministic, meaning they always produce the same output for a given input, or volatile, which means they might produce different outputs even with the same input, maybe because they rely on external state or generate random numbers. The optimizer treats these differently.
And stored procedures, what are they best for?
Stored procedures, which are primarily written in JavaScript within the Snowflake environment, though Snowflake is adding support for other languages like Python via Snowpark, enable you to implement more complex multi-step procedural logic and business rules. Think tasks that involve multiple SQL statements, control flow logic like loops and conditionals, error handling things that go beyond what a single function can easily do.
And these stored procedures in Snowflake support concepts like owner's rights versus caller's rights execution.
Yes, that's an important security aspect. When you create a stored procedure, you can specify whether it should execute with the privileges of the user who owns the procedure, owner's rights, or with the privileges of the user who is calling it at that moment, caller's rights. This has significant implications for security and access control, especially when building automated data workflows or providing controlled actions to less privileged users.
For connecting external applications and tools, like custom Java apps, there's mention of a standard JDBC driver.
Exactly. Snowflake provides standard drivers like JDBC for Java, ODBC for other platforms, as well as connectors for Python, Spark, .NET, and so on. The JDBC driver enables Java-based applications to connect to and interact with Snowflake programmatically, facilitating tasks such as data integration, building custom data applications, table creation, and executing queries from external systems.
Now let's circle back to those data sharing capabilities. They sound like a really innovative and potentially very efficient way to collaborate, maybe with partners or other departments.
They really are one of Snowflake's standout features. Secure data sharing allows you to share live, read-only access to specific tables or views in your database with other Snowflake accounts. And the key is, it happens without any physical data movement or duplication. It's accomplished through Snowflake's underlying architecture and metadata management. The consumer queries the shared data directly from the provider's storage, but using their own compute warehouse.
So the data stays in one place, but multiple parties can query it securely.
Precisely. For this direct share mechanism to work most seamlessly, both the provider and consumer accounts typically need to be on the same cloud provider, like AWS, and within the same region, like us East 1.
What if you want to share data with organizations that don't have their own Snowflake accounts?
For that scenario, Snowflake offers reader accounts. These are special types of accounts that a data provider can create and manage. You can then share data into these reader accounts, and the external entity, the non-Snowflake customer, can log into the reader account to query the data you've shared with them. In this model, the organization sharing the data, the provider, typically bears the compute costs incurred by the reader account when it queries the shared data.
Okay, that provides a way to bridge the gap. Now, to keep track of everything happening within your Snowflake environment, all these databases, schemas, tables, users, roles, warehouses, Snowflake provides something called the information schema. It sounds like a built-in metadata catalog.
That's exactly what it is. The information schema is a system-defined schema present in every Snowflake database. It contains a comprehensive set of read-only views and table functions that provide metadata about all the objects within your Snowflake account. You can query it to find out about databases, schemas, tables and their columns, views and their definitions, users, roles, privileges granted, warehouse usage, query history, loading history, pretty much anything about your environment. It's an invaluable resource for understanding your Snowflake setup, auditing permissions, monitoring activity, and troubleshooting access-related issues.
And for managing the costs associated with those pay-as-you-go virtual warehouses, there are resource monitors. How do they help?
Right, resource monitors are the primary tool for controlling your Snowflake compute costs proactively. They allow you to set limits or quotas on the number of Snowflake credits that can be consumed by one or more virtual warehouses, or even at the entire account level within a specified time interval, like daily or monthly.
And what happens when a limit is reached?
You can configure actions to be triggered when certain thresholds of the quota are reached. For example, send notifications to administrators at 80% usage. And crucially, you can configure actions like suspend or suspend immediately when the quota is fully consumed. This automatically pauses the associated warehouses, preventing further credit consumption and potential bill shock. Careful planning and configuration of resource monitors are crucial to managing your Snowflake spend effectively and also avoiding unexpected disruptions to critical data pipelines if a monitor suspends a warehouse too aggressively.
Snowflake also appears to be a constantly evolving platform, with new types of objects being introduced over time. We saw mentions of sequence objects, file formats, stages, pipes, streams, tasks, and even alerts. These all seem to serve distinct purposes within the broader ecosystem.
Yes, Snowflake is definitely under active development, constantly adding features and object types. Sequences are for generating unique sequential numbers, often used for surrogate keys. File formats define the structure of data files for loading and unloading. We've discussed stages, storage locations, pipes, continuous ingestion, streams, CDC, and tasks scheduling. Alerts are a newer object type that allow you to define a condition based on a SQL query and trigger an action, like sending an email notification when that condition is met. It's useful for proactive monitoring of data quality or system state.
Finally, let's touch briefly on the different types of views available in Snowflake. Standard views, secure views, and materialized views. What are the key differences and when might you use each?
Okay, so standard views are the simplest. They're essentially just saved SQL queries that provide a virtual table based on the results of that query run against the underlying base tables. They don't store any data themselves. The query runs every time you access the view.
So they're good for simplifying complex queries or providing a specific perspective on data.
Exactly. Then you have secure views. These offer enhanced data security, particularly in data sharing scenarios or where you want to restrict visibility. The key difference is that secure views do not expose the underlying table structures or the view's query definition logic to users who only have permission to query the view itself and not the base tables. This prevents users from inferring information about the underlying data they shouldn't see.
So better for security and governance. Any downsides?
They can sometimes have limitations regarding how the query optimizer can work with them compared to standard views, potentially impacting performance in some complex scenarios, but they are crucial for security. Lastly, materialized views. Unlike the other two, materialized views do physically store the pre-computed results of the view's query.
So they cache the results.
Essentially, yes. This can significantly improve query performance, especially for complex aggregations or joins that are accessed frequently, because Snowflake can just read the stored result instead of recomputing it every time. However, they come with trade-offs. They incur storage costs because they are storing data, and they require periodic refreshing, which also consumes compute credits, to ensure the stored results stay up to date as the underlying base table data changes. So use them strategically for performance bottlenecks.
It's always helpful to see how these technologies are applied in the real world. The information you shared highlighted use cases in sectors like advertising, media, and entertainment. For instance, Warner Music Group leveraging Snowflake for better audience analytics and personalization efforts. And also this concept of privacy-preserving data collaboration through data clean rooms.
Yes. The ability to handle massive data volumes, perform complex analytics at scale, ingest diverse data types easily, and securely collaborate with partners are key drivers for adoption in these industries. Data clean rooms, in particular, are a powerful application of Snowflake's data sharing and security features. They allow multiple companies, like an advertiser and a publisher, to join their sensitive data sets and gain combined insights without either party having to expose their raw customer-level data to the other. It's all done securely within the Snowflake environment, adhering to strict privacy regulations.
Fascinating. So it enables collaboration that might otherwise be impossible due to privacy concerns.
Exactly. And of course, beyond media, Snowflake's versatility makes it a core data platform for general warehousing and analytics across a vast array of other industries: retail, finance, healthcare, manufacturing, you name it.
Okay, let's try and unpack what we've covered in this deep dive then. Listeners should now have, I think, a pretty comprehensive understanding of Snowflake's cloud-native architecture, its unique three-layer design.
Right, and its core features like the independent scaling of compute and storage, those powerful capabilities like time travel and zero-copy cloning.
The various mechanisms for data loading like copy NTO and Snowpipe, and how transformation happens using things like streams and tasks.
And critically, the importance of the security model, RBAC, encryption, network policies, and especially the user's responsibility, highlighted by the need for MFA in light of recent threat campaigns.
Plus the power of extending Snowflake through programmability with UDFs and stored procedures, and the innovative data sharing features.
Yeah. Now here's where it becomes truly insightful, I think, for you, the learner. Consider how this cloud-built design and the specific array of features directly address those perennial challenges we used to face with traditional data warehousing.
You mean things like the scalability bottlenecks, hitting limits on hardware?
Exactly. Those bottlenecks, the sheer complexity of managing and tuning those older systems, the constant struggle for robust security, and the often delayed demand for timely, actionable insights. Snowflake's approach, you could argue, really aims to democratize data access and analysis. It provides a platform that seems adaptable to varying levels of technical expertise while still offering a really sophisticated toolkit under the hood.
So what are the implications for someone listening? Whether you're grappling with specific data challenges right now, maybe evaluating new technology solutions for your company, or perhaps just expanding your understanding of the modern data landscape.
This deep dive should provide a valuable framework, hopefully, for assessing the potential of modern cloud data warehousing platforms like Snowflake, the ability to independently scale compute and storage on demand, the baked-in data protection mechanisms like time travel and masking, and the automation possibilities offered by things like streams and tasks. It paints a pretty compelling picture for boosting efficiency and enabling more data-driven innovation.
Which brings us, I suppose, to a crucial question for you, the listener, to ponder. Given these capabilities we've discussed, the scalability, the security, the automation, the sharing, what specific areas within your organization or your domain could stand to benefit most from the flexibility and power that a platform like Snowflake provides?
Is it maybe achieving faster analytical processing times? Is it enhancing your data security posture and governance? Could it be streamlining those complex and often brittle ETL processes? Or perhaps unlocking completely new opportunities for secure data sharing and collaboration with partners or customers?
Lots to think about there. Well, thanks for taking this deep dive into Snowflake with us today. We trust that this exploration has provided you with both clarity on the platform and perhaps sparked some further curiosity. The world of data is constantly evolving, as we know, and Snowflake's dynamic platform certainly offers a multitude of exciting possibilities to explore further. Thanks for listening.